Today, I want to talk to you about my favorite group of numbers. But first, we need to define what groups we have in the first place. Mathematicians started with the most basic group of numbers, the natural numbers, 0, 1, 2, 3, 4, 5, and so on. We can extend this to the negative numbers, and this new set is called the integers, or whole numbers. It's written with a capital Z. It stands for Zahlen, the German word for numbers. We can do some division with these numbers, but some results are not whole numbers. Instead, they are rational numbers. Each of these can be written in the form of a fraction with two integers, i.e. a ratio, hence the name. This is how you define it professionally with fancy set notation. By the way, the Q stands for quotient, which is the result of division. Usually you then move on to the real numbers, which includes irrational numbers like pi or e, and then to the complex numbers, which include the square root of -1, written as I or rarely also as the Greek letter iota. Thanks to I, a lot of expressions which were previously impossible to calculate now have a value. You can even calculate its square root. Complex numbers are fascinating in their own right, but this video is not about them. I'd like to now introduce a few more interesting number groups. The constructible numbers have lengths which can be constructed using only a pencil, compass, and straight edge, a ruler without marks. This group includes the square roots of 2 and 3 and phi, the golden ratio. The algebraic numbers include all numbers which are the zeros of polynomials with integer coefficients. So for example, all numbers x, such that x cubed minus 3x squared plus 8x minus 12 equals 0. Here we have the cube roots, among others. Numbers which are not algebraic are called transcendental. They include classics such as pi or e. Finally, we can create the biggest group in the real numbers, the computable numbers. These all have a finite set of rules which describe how to calculate them. Even if it would take an infinite amount of time to fully carry them out, the rule set can be written down on a finite space. An example of a non-computable number is Chaitin's constant, the probability that a random computer program will halt at some point. But my favorite number group is much smaller, the rational numbers. I like how they're not as simple as the integers, but not as open-ended as the irrational numbers. Firstly, did you know that all rational numbers have a decimal expansion that's either finite or recurring, but never infinite? This is very easy to prove. Let's take 6/7 as a simple example. If we do long division on this fraction, you can see that we have different remainders down here. Now consider this. There's a finite number of remainders that we can get, from 0 up to the divisor -1, in this case 6. If we somehow got the divisor or more, or a negative number, then we must have made a mistake in the division. If the remainder at some point is 0, then the decimal expansion is finite. If not, then we'll go through, at worst, every single other remainder until we end up with one we already had before, which in turn will lead to the exact same chain of remainders. Therefore, the decimal expansion is recurring. Now let's compare the naturals and the integers. Both sets are infinitely large, although it seems like the integers should be twice as big as the naturals, since there are also the negative numbers. It made me think, in theory, how much bigger is the number of rational numbers? Keep in mind that this question doesn't really make sense, since infinity times anything still equals infinity. We can write all rational numbers in the form p over q, where p and q are integers. To find the multiplication of infinity for rational numbers in a logical way, let's go step by step and find the number of rational numbers in this form, where p and q are both smaller than some number n, and then see how the number of numbers changes as we increase n. So, how many different rational numbers can we get where the numerator and denominator are both smaller than n? For the sake of simplicity, I'll only consider positive numbers. Let's start by just writing them out. For n equals 1, the only fraction we can make is 0 over 0, which doesn't have a value. For n equals 2, we can make 0 and 1. For n equals 3, we can also make 2 and 1/2. Note that we only write 0 and 1 once, even though we can write both in two different ways. As we continue writing these out, you might notice that there is actually a pattern. We can order these numbers as all the integers up to n-1, then all the fractions with 2 in the denominator, then all with 3 in the denominator, and so on. What can we say about the numbers in the numerator then? Well, we have 1/3, 2/3, 4/3, 5/3, 7/3, but not 3/3 or 6/3, since we already wrote them down as 1 and 2. The difference between them is that these share a factor between the numerator and denominator, namely 3. Therefore, they can be simplified, which means we shouldn't add them to our list a second time. Two numbers which don't have any common factors, apart from 1, are called coprime. So we can describe the value of our function as n plus the number of numbers smaller than n and coprime with 2, plus the number of numbers smaller than n and coprime with 3, and so on up to the number of numbers smaller than n and coprime with n minus 1. It sounds quite complicated, but it works, and I think it was a fun exercise.